control in an electric vehicle battery using transfer function modeling. We know that in this fast world, electric vehicle plays a vital role in automation industry. In this, the electric vehicle battery plays a major critical factor. So if a battery is too hot means the performance of the vehicle will be reduced. At the same time, the efficiency of the system will automatically reduced. In extreme cases, the thermal runaway will be occur. So for this, we need to model the mathematical modeling of battery transfer function in control systems. So now let us see the problem statement in a case study.
The problem statement is simple but yet serious. So when the EV batteries are charging, the heat is generated. So we need to reduce this heat with the help of a cooling system like a fan or a liquid cooling system. So how do we know how much the temperature rises, how much cooling is needed, and how the system responds to the sudden load changes? So for this we need to create a mathematical model for the thermal system.
Salman and I'm going to explain about the system modeling. Before getting into that, we must have an equivalent circuit of this proposed solution to come with a mathematical model. For that, we are considering an electrical RC circuit so that the capacitance C acts as a heat storage element and R acts as a heat transfer element, that may be a fan or a coolant oil, etc. So with the RC electrical equivalent circuit, we can construct the following equation. Energy the equivalent electrical circuit, that is RC, we can construct the energy balance equation. We know that the capacitance element is the heat storage element and resistive element is the transfer element. So from the balanced equation, the heat input, that is the stored input, is capacitor element is equal to the stored heat and the heat loss. So that we can combine this equation to form into a differential form, that is CdT by dt, that is change in temperature with respect to time and change in temperature with respect to the resistance. Okay. And the Qt is the heat loss. We can take Laplace transform, that is we have to convert this domain from time domain to S domain so that we can obtain the following equation, which is a first order equations. So in conclusion, in the mathematical model, this heat monitoring and heat transfer function is a first order reaction, first order equation.
So I'm going to speak about the block diagram, how does this EV work and how does this control the temperature. In this block diagram, first there is Q heat input, then it goes to the thermal model, then it will go to the temperature. So let's take an example. An EV is climbing up to a hill. It's going on a hill. The EV vehicle accelerates its speed. So due to this, the current will increase. And if the current increases, then the heat will also increase due to the increase in the current. So in this this comes into the thermal model. In this, RS acts as a time response. If the RC is greater, then there will be less thermal cooling. If the RC is more, then there will be and greater RC is less, then there will be a higher temperature cooling. If the RC is more, then there will be lesser temperature cooling. At the end it will get into the temperature and will cool down the temperature of the EV.
So now let us see about the real life applications. So in real life, the temperature modeling is very useful in electric vehicles. So when an electric vehicle is running or charging or climbing a hill, the battery will get heat. So if the temperature of the battery is too high, then the battery performance reduces and it may get damaged. So therefore a temperature controlling is very much needed here. By using the transfer function, we can calculate how fast the battery will get heat and also design a cooling system, and we can also predict what type of cooling system is needed, such as a fan or a liquid cooling system. So instead of using a physically testing every batteries, we can use simulations. So therefore this system helps the engineers to build a safe, efficient and a low-cost battery system.
In the simulation results, the engineers have observed that there is an exponential rise in the temperature. So after some certain period of time, the steady state is reached. So from this, we can observe that there is heat input increases, temperature also increases. So by using the transfer function modeling, we can predict the system behavior so accurately.
Conclusion, this case study shows how the overheating in batteries in EVs can be represented using mathematical modeling and transfer functions. So by forming energy flow equations and taking Laplace transform, we form and derive the first order transfer function, and which helps us to quickly predict how fast battery's temperature changes. And therefore, control systems concepts are not just for theory, they play a practical role behind EV safety and performance.